Right. So we don't want autocorrelation for our UIs. The assumption says that there should be no autocorrelation in UIs, right? That's the relationship. That's what we want. So given any two x values, xi and xj, the correlation between ui and uj is zero, right? So that's the assumption that if we have one value of x and another xi and another value of xj, the correlation between ui and uj is zero. In short, the observations are sampled independently. We can write it symbolically like this: covariation or covariance ui between ui and uj given xi and xj is zero, right? So covariance is zero. If x is non-stochastic, that's what we assume, that x is fixed. This should be zero. I and j are two different observations where covariance, COV means covariance, right? So do you have any question on this? Should I expand it a little bit more or did you get it?
So again, what is the difference between correlation and autocorrelation?
Okay. So let me give an example here in this particular frame of reference so that you understand both the things together, what is being said in this assumption and what is the meaning of autocorrelation. So we have x here and y here, and we have one value of x, say xi, and another value of x, say xj, and we have some y's for xi and some y's for xj, and we have a regression line. And of course, the vertical distances between each of these dots and our line are the UIs, right? Some UIs are positive, some are negative in both the cases. UIs are corresponding to XI and you can call them UJ corresponding to XJ. This is one set of U's. You can call them UIs. These are corresponding to xi, and corresponding to xj you have another set of u's. You can call them uj and you can record them here. Now ui or uj, they are ultimately u's or errors. So the variable is u, right? There's a set I and set j. From set of values of u, one set is called ui, another set is called uj because they are corresponding to xi and xj respectively, right? If you if you calculate covariance or correlation between ui comma uj, and of course this is conditional correlation or conditional covariance because we are calculating this for a given xi and xj. So if this covariance between ui and uj turns out to be zero, then we would say that there is no autocorrelation across or within errors. U's are not related or correlated with other U's, right? So that's why we made two sets, UIs and UJs. UIs are corresponding to XI, UJs are corresponding to XJ, and because they are not related at all, there is no systematic variation between UI and UJ, so that their covariance, conditional upon the given values of X, is zero. It is neither positive nor negative. That means if UIs are big, if UIs are big numbers, then you cannot say anything about UJs, whether they will be big or small. If UJs are big, you cannot say anything about UIs, whether they will be big or small. That's what the interpretation of zero covariance, right? So if this is the case, this is called autocorrelation because of the fact that ultimately we are trying to see correlation between errors, right? So this variable and this variable are not two different variables, but they are, these two are the same variable called errors. That's why we call it autocorrelation, right? That is the answer to one question. And the answer to another question, the meaning of this assumption, you can understand by this example, this graph, and this notation, right? Now, why this word correlation is used here, and then covariance is used here? Actually, you can use them interchangeably, covariance and correlation, when you are only interested in knowing three things: whether two variables are positively related, whether they are negatively related, or they are not related at all. So covariance is zero. So you want to differentiate in these three things only. Or let us put these two things together, positive and negative, or zero. So there are two options or two possibilities that you're looking for, whether there is any covariance, whether positive or negative, or there is no covariance. So that covariance is zero, right? In that case, you can use these two concepts interchangeably. So that's what we are interested in. We just want to know whether covariance is zero or whether it is non-zero, right? Positive or negative. That's what we are interested in. And that's what we have written here in notation, that this should be zero. If it is zero, we are fulfilling the assumption that there is no autocorrelation between the disturbances, to be put in notational form like this, right? I think it's clear now.
Yes, so you basically want to say that two disturbances should also be independent of each other.
Two disturbances should be independent of each other. That's another way of saying this, the same thing, that the two disturbances are not correlated with each other, or
So, sir,
they do
why
not
are we using the
co-vary
word
with each other.
autocorrelation?
Yeah.
So, sir, why are we using the word autocorrelation? Also, sir, I think so somebody is trying to join in.
So that's what I just told you, that you can, I just expand on this fact, that why we call it correlation and covariance, why do we use them interchangeably. I just expanded this idea. Should I repeat it?
Yes, sir, maybe that helps. And, sir, somebody is trying to join in.
All right, so I'm repeating the same explanation again. So we can use covariance and correlation, these two terminologies, uh, interchangeably, if we are interested in knowing only uh, the two the possibilities of zero correlation and non-zero correlation. So that is the same thing as saying zero covariance and non-zero covariance, right? So we can use them interchangeably if we are if we are expected to know only this much, right? So we are not interested in knowing how much. Is it 0.8? Is it 0.6? That is the level of correlation, or it is weak correlation 0.1, right? We are not interested in the strength, right? We are only interested in saying that there is no correlation or there is some correlation, non-zero correlation. So that's why we can use them interchangeably, right? Did you get it now?
Yes, sir. So, your two terms which you're talking about are are correlation and autocorrelation, or
No,
correlation and covariance.
correlation and covariance.
Yes, sir. That I understood. My question is, what is the meaning of autocorrelation and how is it different from correlation? I understood that difference prior only.
Okay, so you have to put your questions, very precisely what you want to ask, right?
So sorry, sir.
Yeah, you should be very precise when you're asking question. Don't ask long questions. Just put it very short and straightforward, right? So you are asking what is the difference between correlation and autocorrelation, isn't it?
Yes, sir.
That's what you are asking.
Yes, sir.
Okay, okay. Correlation is the strength of linear association between two variables, x and y. Autocorrelation is also the strength of linear association, but not between two variables, but between the values of the same variable x, right? So here in this case, we are talking about one variable, and that is the errors. And we are trying to see whether the values of errors are related among themselves. That's why we are using the term autocorrelation. If we use the word correlation, it would mean that there are two variables and we are trying to see whether these two are linearly related to each other. Got
All
it?
right, sir. Got it.
So that's the point. Uh, Again, let us not go into the implication, which is very important to understand. Implication of this assumption. Why do we need this assumption? What is the importance of this assumption? What happens if it is violated? How do we know that this assumption is violated? How can we correct it if it is violated? There are a lot of questions that need to be answered, and they are very important questions, but we will not touch upon these uh, because we will touch upon these questions when we will study violation of assumptions in another unit, right? So I'm not going into that. So here I just want you to understand what is the meaning of this assumption, and that's it. All right. So you can see that u is here, u is here. We are talking about u and u. It should be x and y, right? To be called as correlation, but this is u and u, so we call it autocorrelation, right? Relationship with itself, autocorrelation between u and u, right? Anyways, if the plot looks like this, if you plot all the errors, and if the plot looks like this, that means there is positive autocorrelation. If you plot all the errors and the plot looks like this, you can call it negative autocorrelation. If you plot all the errors and the plot looks like this, you will call it zero autocorrelation. This is what is good. This is what makes us happy because we want the scheme of things to look like this. We want our errors to look like this, right? We don't want this and this. That as per assumption 5, right? All right. So do you want me to expand on this more or did you get it? This one, this graph.
So got it.
Anyone else?
So I got the graph. So can you please tell the assumption 5 once? Like I didn't understand the assumption.
Okay, you want me to repeat assumption 5?
Yes, sir. So, cause when Priyank asked, na things got a bit like confused.
Uh-huh.
So when Priyank asked, so I forgot what was the main thing which was focusing on assumption 5.
Okay. Okay, so I'll repeat assumption 5 again, but I'll go a little bit quickly. All right, so this is okay. Okay, if you want to ask a specific question, you can ask in this assumption, or do you
Oh,
want me to explain
so
overall?
basically I got the meaning of autocorrelation. So, but
Hmm.
what is the meaning of no autocorrelation between the disturbances? What does this mean? I wanted to know that.
No autocorrelation. What is the meaning of no autocorrelation between the disturbances?
Yes, sir.
Okay, so that means this is everything that we have in assumption 5, right? That's the gist of everything.
Yes, sir.
All right, so this is the assumption which says that if you have UIs and you use, if you have use, if you divide these U's into two parts, you call one set as UI, another set as UJ on the basis of that UI is corresponding to a value xi and UJs are the errors corresponding to a value xj, right? As you can see in this graph here and here, these are the two sets of U's, right? Uh, and if you write them in two columns and then you calculate the covariance, right? Uh, you can calculate covariance using a very simple formula.
Sir,
UI,
hello.
yeah,
So actually, Stuti is trying to enter since a long time. Could you please let her in? She had connectivity issues, so she's joining from another account, I guess. Thank you so much.
right. So if you find covariance between the two, there is a simple formula for that. You can see it yourself, that formula. It's simply you have two variables x and y. You can find xi minus x bar times yi minus y bar and then add the product and divide by n. What you get is the covariance. And if you divide the covariance by the product of standard deviations of the two variables, what you get is the correlation, right? So these are two simple formulas, but let's not go into the formulas. The concept is that both of them tell us about the strength of linear association. So if these two, ui and uj, are correlated with each other, if there is non-zero correlation, we are violating this assumption because what we want is no autocorrelation. That means what we want is that covariance ui comma uj should be zero. So there should be no covariation between ui and uj, right? No correlation between ui and uj. They should not change or vary together. The variation should be random, which is evident in this third graph. If you have a look at the third graph, can you say that if what is there on the x-axis? Uh, okay, let me change it a little bit so that you understand it better. I'm changing this I to j and this I to j, right? So we have ui's on the x-axis and uj's on the y-axis. And then ui's and uj's, if somebody asks you, okay, look at this graph and tell me if ui rises, what happens to uj? What will be your answer?
So we can't define that. Here
We
we
can't
can.
say anything,
Yes, sir.
right? We can't say anything here. But if somebody asks you here, if UI rises, what happens to UJ?
So it declines.
You can say UJ falls.
Yes, sir.
In this graph, if somebody asks you if UI rises, what happens to UJ?
So in the first one,
Yeah,
sir, it increases.
UJ rises. So you are clear that if UI rises, UJ will rise. Here
Yes,
you are clear if UI rises, UJ will fall. Here
yes,
you are not clear. If UI rises, what happens to UJ? You can't say anything. It could be anything. It could rise, it could fall,
yes, sir.
right? It means covariance between UI, comma, UJ is zero. Here you would say covariance between UI and UJ is negative. Here you would say covariance between UI and UJ is positive.
Okay, sir.
So we want this to happen. This is our assumption. This graph is what is good. We are happy if this happens. That's what our assumption is all about, right? That there should be no covariation between UI and UJ.
Okay, sir.
Yeah.
So can you please tell that the formula you told for covariance was xi minus y, that because it was not shown on the screen.
Where?
Sir, like in the last slide you were writing the formula. No, there's a bit of lag in the pen when we see it, the writing na part, because it lags a bit in between.
I did not write the formula. Do you want me to write the formula?
So yes, a relation between covariance to and correlation, that one that you were telling.
You want me to write a formula for covariance and correlation, right?
Yes, sir.
Okay. So, okay, let me write it here. If you want to find, if you have data x, y, and you want to find covariance x comma y, right? Then what you would do is take each x value, subtract the mean of all x's, multiply it by the same for y, add the product, divide by n, you will get the covariance, right? If you want correlation between x and y, find the covariance between x and y, put it in the numerator, divide it by the product of standard deviation of x and standard deviation of y. You would get correlation. So because now you have asked me to expand on the formula also, so let me say a few more things now. Uh, what is the numerator of correlation? Covariance, right?
Yes, sir.
Standard deviation is always positive, remember? Always positive. So denominator is always positive. Correlation can be negative only when covariance is negative. Correlation will be positive only when covariance is positive, because covariance appears in the numerator of correlation and the denominator will always be positive, right? And correlation will be zero only if covariance is zero. So on the basis of this understanding, you can use covariance and correlation interchangeably when you are interested in knowing whether there is zero covariance or correlation and non-zero covariance or correlation, right? Here in this autocorrelation assumption, we are exactly interested in knowing this fact whether covariance is zero or non-zero. So we can use the word correlation and covariance interchangeably, right?
Okay, sir.
So, of course, there is, if you want to understand it better, you can go ahead and read more about covariance and correlation yourself, because this is not the right platform for me to expend that much on covariance and correlation. Of course, there is a lot to understand, but this much is more than enough uh, here in this particular topic. But it would be great if you understand it better, right? Any other question?
No, sir. Thank you
Sir,
very much.
uh,
Yeah.
yeah. So actually, my question is that what do you tend to imply by it? Like, what do you like? What if this is not true? How will it impact our results?
That's what I said. That's why I said it before, that there are many questions which are not answered here now, right? And I'm making them clear. All the question. One of the question, it is one, the question that you are asking also falls in that category. That point number one, let's talk about autocorrelation only. Uh, what is the implication? What are the implications of having and not having autocorrelation? What does it stand for? How does it affect the results? Uh, how do we detect it? What are the causes uh, of autocorrelation? Uh, how do we correct it? Many important questions unanswered here, right? So let's not go into these questions. It will take us very far into autocorrelation, right? So when, of course, we will be talking, I will be talking to you about all these things in great detail in this course itself, but not now, right? There's another unit. It is called violation of assumptions. Let me show you that unit. Unit 4, relaxing the assumptions of classical linear regression model, introduction to multicollinearity, heteroscedasticity, autocorrelation, the nature of the problem, its detection, and corrective measures. So we will have three topics here. Number one, multicollinearity. which is not yet introduced. I'll introduce it as the time comes. Then number two, heteroscedasticity, already been introduced but not dealt with great detail. But here we will deal with it in great detail. Topic number three, autocorrelation. We will talk about autocorrelation in great detail in unit 4. Only 3 topics to be covered here in 15 hours. Right? So I'll be spending 5 hours on multicollinearity, heteroscedasticity, autocorrelation. So 5 hours of autocorrelation, right? There we would discuss these things and I will answer all your queries and questions which go a little bit deeper into the problem of autocorrelation. Got it? Right?
Yes, I got it.
All right. So then two more assumptions, very simple. Assumption 6 and assumption 7. Assumption 6 says the number of observations must be greater than the number of parameters to be estimated. Alternatively, the number of observations must be greater than the number of explanatory variables. So if you have a model, simple regression model like this. So there's one explanatory variable. So if you are collecting data on Y and X, you should have some observations, and at least the number of observations should be greater than the number of parameters to be estimated. So basically we will be estimating 2 parameters here, beta 1 and beta 2. So you should have 3 observations at least to meaningfully run this regression. This is assumption 6. This is highly simplistic, but because it was required to be mentioned, so it is there. Sort of understood type of assumption when you're running a regression. If suppose you have a point and you want a line, your line could be here, it could be here, it could be here. So there are infinite possibilities. If you have 2 points and you want a line, of course, line will pass through both the points. So there are no errors. So one observation will not do anything. It's useless. 2 observations also useless because your line would pass through both the points. So no errors. Errors would be 0. So there is no point running a regression like this. If you have 3 points, then you would have a line and there would be errors also, right? So at least 3 observations is what you require to be put in in the form of a rule. Assumption 6 can be taken for granted that n must be greater than the number of parameters to be estimated, which you can see from here. There are 2 parameters to be estimated, beta 1 and beta 2. So if you want observations to be greater than 2, then at least there should be 3 observations, which is clear from this example also. Then assumption 7 says that the nature of x variables, the x values must not all be the same, right? Technically, variance of x must be a positive number. Furthermore, there can be no outliers in the values of x variable. That is, values that are very large in relation to the rest of the observations. 3 points here. Let me clarify on all the 3 points one by one. Point number 1. X values in the sample must not all be the same. So, of course, if you are collecting a sample and you want to run a simple regression between x and y, and suppose you have some values on y but you have the same value for x. That leads your x to be fixed at 3 and your y's to vary all over the place. And now you want to fit a line. The line can go from here, the line can go from here, the line can go from here. Doesn't make sense. Any of these lines is a good line. All of these lines are good lines. So the uniqueness of the line is gone, right? Because there are many lines possible if the value of x is fixed at 3. So regression does not make sense. That's why the assumption is there that the x values must not all be the same. So variance x must be a positive number, point number 2, because this point leads us. Now, what is the variance of x? All the values are 3. So variance of x is 0. There is no variation in x, right? So when variance of x is 0, regression is not meaningful. So you have to have some variation in x values to be able to run a meaningful regression. Point number 3, there can be no outliers in the values of x variable. So when we talk about x values being fixed, so we have this value, this value, this value, and this value. And suppose we have nice looking data here, and we are ready to fit a line like this. But again, you got one x value here, and then there is some data here. Now this is disturbing because it is letting your line to go from here. It is asking you to draw a line from here, right? So it is disturbing everything. So we don't want our x to have outliers, right? So outliers in the x values are disturbing, right? So we don't want our x to have outliers. That's another point that has to be taken. Now this assumption 6 and assumption 7 are sort of not that much technical. You can say these are, peripheral assumptions. I'm not saying they are not important, of course. We need to understand that these are the things we need to take care of along with other important things. These are also important, right? But these are assumption 6 and assumption 7 turn out to be um, very simple and basic assumptions.
Excuse me,
And
sir.
we need to, of course, they need to be fulfilled also. Yeah.
Sir, could you please repeat the second and third point for the assumption 7? The positive number and outliers.
Okay. Variance x must be a positive number. It is saying, it is just putting the same point number 1 in some other words. So if xi is equal to 3 and it's not changing, then if you calculate the variance, what is variance? Xi minus x bar squared added divided by n minus 1. It turns out to be 0, isn't it? It will be 0. You can calculate it yourself, right? So because numerator will be 0, right? Okay, let me show you. Do we have some time? 5 minutes? Yeah, we have. So all the values are 3. Tell me what is the mean of these values? Mean of x bar 3. Because all values are same, the mean will be the same, right? So what is xi minus x bar? 3 minus 3, 0. 3 minus 3, 0. 3 minus 3, 0. Add all the zeros, it will be 0. Variance is equal to summation xi minus x bar squared. If you square these, they will again be 0, right? Squared divided by n. So numerator, sum of xi minus x bar squared will be 0. So numerator is 0 and 0 divided by n is 0. So the variance of x is 0, right? So we don't want our variance of x to be 0. In other words, we don't want our x to be same number all the time. We want some variation in x. So that variance is positive. If there is any sort of variation in x, for example, 3, 2, 3, 3, 3, 3, 2, there are two twos here, suppose, then variance will turn out to be a positive number, right? That's what it is written here. Variance x must be a positive number. Then the last point is there should be no
Yes, sir.
outliers. It just tells us, the last point tells us it is advisable and it is good to have our x values, fixed x values, uh, close, I mean, um, in continuation. It should not be like this, that there is a continuation of some x values and then we have a discontinuation for a long distance and then we have our one more x at the end, right? Because then this set of x values and this one single x which is far away from this set of x values, it will be creating problems because this, the only x, this outlier would force our regression line to tilt, uh, and then the weightage of these observations, all lot many observations here, uh, would be disturbed, and this will outweigh these observations because this will force our line to get tilted towards itself, right? So we don't want outliers in x also. Got it?
The third point, sir.
Did not
So
get
what
it?
do what do you mean by outliers?
Okay, outlier is an observation in a data set which is very big or very small in relation to other values. That is an outlier, right? So if you have values of x like this, 2, 3, 2, 4, 5, and then you have a value 29. This 29 seems to be an outlier, right?
Yes, sir.
So this is outlier and we don't want outliers in x, right?
Got it, sir.
Yeah. All right, so we stop here. Uh, Continue reading from the book, and whatever questions you have, you can ask in the classes as you are already doing. So it's great. Uh, let us stop here.
Thank you.
Please, Priyank, please send me the list of absentees on the
Yes,
WhatsApp.
sir, I'll send that. Thank you, sir.
Okay. So thank you. We'll continue next time. Thank you. Have a nice day.